Hello guys, welcome to this video. So in this video we're gonna go understanding the score matching in diffusion. So we are we are in the journey of learning diffusion models. So we started from the introduction of diffusion models, and then we move on to the processes of diffusion model, which is forward and the reverse processes, and then we uh, after that we understand how can we improve the DDPM by learning variances and improvising the schedule of the noise schedule and other other details. How can we improve the DDPMs? And I am just taking you into the new realm, which is a score matching. And this is a pretty. This is not a recent approach, isn't it? The score matching is really a very old approach, isn't it? And it has been applied in various fields in statistical physics and thermodynamics, but this score matching, it is this is we are you can just think of like we are in this is and this is our diffusion route we are going through. So and this is a score route. So it's a score route. This is a diffusion route. So this is something this mix up is, and this is like a we are going into the diffusion journey, and this score, this is this traditional things comes and merge here. So in diffusion model, and it is very strong, and this has a very strong application in the diffusion also, and in the other generative modeling spaces. So in energy based model and in autoregressive and other other you can also apply the this score matching uh, techniques is in other generative model also, but we are gonna focusing on primarily on the diffusion model because we are in the journey of learning diffusion models. So I want to give you this in a much more detailed way. So how can you learn this score matching in the case of diffusion model? So we're gonna look at. So we'll take time and we'll understand each and every component of it. So let's start. And so if I can show you. So the score matching. So what is the score and what is the score matching? We'll understand it as you go forward. But but let's start with some of the important questions. So we'll understand later on what does this mean score and what does this mean score matching. But before going into that, just take some of these question to go there. How do we represent it a probability distribution? So in autoregressive models, we represent it like this, and in other models, so we are in the question of how we represented a probability distribution in the previous model. So this is our we define this p theta, which is a distribution. So we define the distribution like this: the cumulative product is any of this p theta of xi given xi just previous less than I, and so and then in flow models, and in full flow models, because we doesn't have read it, but then we define the probability this as this, and this is the different as in different models we represented the probability densities in different formats. So in in VAE we will represent the p theta of x like this, and so in our journey we define this quantity as differently. In energy based model we define this in this way, and this is actually a defining. So this is an explicit approximation of p theta of x. So this is explicit. This is explicit means we are directly estimating this p theta of x in some sense. So in this is explicit, but in a little bit implicit way, like a GANs. So like a GANs, we doesn't approximate this, but we will just make. So in GANs, what we do is we have a generator. This is generator, which is a functions. You can just function, which is a functions, and this is actually a transformation functions. So this is a transformation functions, and it will take this Latin vector input, some set of numbers, it can be a 100 dimensional set of numbers, and if you pass through this function, it will generate images. It will generate images, 2D two-dimensional images, which will mm, which which look similar to what we have in the data set. So we have to learn this function. This neural networks are very good at learning functions as we know it. So this transformation function will learn by the neural network, and this is we are not explicitly defining p theta as an p theta of x, which is nearly equal to the real data distribution. So p of x means the data distribution. So you can just assume that this is a data distribution. Uh, and what is data distribution? And distribution is, you can just consider like this, is in if you take the symbol distribution, so like a distribution, so so if you take some of the points here, the maximum the likelihood of being the likelihood of being data is higher, so here the probability is higher, the falling of data here in this distribution is higher. So we'll define the probability distributions p theta as like this is one dimensional Gaussian distribution. So and this is an implicit way of uh, doing generative defining the generative models. And so I want to again focus on this quantity here. This quantity is actually called the normalizing constant, and which is interactable, and this is the hurdle main hurdle of the whole generative processes. So in generative, this is very, it's interactability, and it's hard to compute, and we want to just get rid of it as in this all these above approaches. We use some of the techniques and some of the trade-off we make to get rid of this quantity, this in above also. And in this we doesn't have to deal with this normalizing constant in the generator, because we are just doing transformation of the Latin variables. So, and this is a good time, isn't it, to understand what the score function is. And so, score function is defined as the gradient. So, this is our probability density, and it could be the density of this should be a probability distribution of images of dog. So, you can just imagine this is the probability distribution of dog, and it- and if you consider it, it is high dimensional, and it is very hard to approximate, and this is the distribution p theta of x and p of x, and this is the distribution which has millions of dimensions. So if you take 225 cross 225 cross 225 images dimension, if I take this resolution of images, so this will result in, so if I do multiplication here, so if I do multiplication here, so 225 into 225 225 into 3, so that I think this is as a main variation in high dimensional images. If you just consider the resolution like this is channel and this is height and width. So this image is actually a high dimensional image. And, and it has many dimensions, not just one dimensional, but it rely on a high dimensional spaces. So, and this is hard to compute, isn't it? For model to just if you start from the simple and try to approximate this, isn't it, and try to changing it and approximating it, isn't it, by some neural network, if you start approximating this with this, and it is very hard, and this is very notoriously difficult task to even to practice and do some test on, isn't it? So this is a data distribution p of x, and and this score function is the different approaches, isn't it? So we can't determine this p of x, isn't it, which is very difficult to model. So what we do is first we define a score function. A score function is defined as a gradient of the log likelihood, isn't it? Log likelihood with respect to the data vector x, and given by, so this score function we define is s of x as a gradient. So gradient means this gradient of log of gradient of the log likelihood of the data. So this is the it will give probability values, and we'll take the log likelihood. So and we will do grade we'll take the gradient with respect to data vector x. So this is the score function. So and this is not dependent on any model parameter, and this is with respect to the data, and this is actually a vector valued function. So if we take this, it will give a set of vectors in a vector valued functions. So I want to write it. This is a vector valued functions, and if we take the gradient, so and it will give something like this score functions. So scalar function p of x is actually this will give some scalar value p of x, some probabilities, and so if we are here, isn't it will give the highest probability here, and it will also give if you take some random variable x and put it into this p function, and it will give some scalar value, and if you differentiate with, and it will give the directions in which you have to move to maximize this. So it will give the direction where there is a density of where there is a high density. So let's and this is the score function, and the gradient with respect to the data vector and not with respect to the parameter vectors, and is a vector valued function of the same dimensionality as x, so that each element is, so if you each element of this vector valued function is given by this quantity s of x is equal to minus of ln p of x. So this is a partial derivative, so that so we'll take this, we'll differentiate like this. So if we take the images like this, two-dimensional images, and this image has some certain pixels, so it has certain pixels, so it has certain dimension. This is the dimension of the images, and if we and this each element, so if you this is the images and this is your score, so we can just compare the score and images. This is the data which has certain dimension, and this is the your score, and the dimension of this score and the dimension of this images will be the same. So this is, and each element of this score is defined by this. So we will take the derivatives with respect to, will differentiate each element with x of I with this ln p of x, and x is the ln p of x divided by this particular pixels, you can just consider it. So and this is the scores, and you get, so is associated with the corresponding each element of xi of x. So where x is an image, then s of x can be represented, so s of x can be represented as an image of the same dimension with corresponding pixels. So as written here, if we take, if x is an image, then s of x will represent and represent as an image of same dimension with corresponding pixels. So this is the score is in a function. So if you, so overview of the score functions, and so if you took on to look at the visual as in what is a score function, so if you have the this is if you, this is a score function, if you have p of x, and it is actually, if you consider this image, this is if your data is multimodal, means it has two modes as here. So if you have two modes, so if I can, so if you have two mode, and so if you have two modes, and this is the points here you're giving. So this is the this point, and this is also, it should be smaller than enough. So if I can just clear this, so this point is higher, so this peak is higher, and this is smaller. So this quantity will represent this here. This is the density, the probability of this, and this is represent this quantity here. So so if you differentiate this quantity p of x, you will get the vector field is in like this, and this vector field is actually giving the directions directions of the this peak direction where the data is, where your data lies, isn't it? So where the maximum values of this quantity p of x lies. So if you take the one dimension, it will give the direction like this. So if you started from somewhere here, and if you started something you are here, so it will give the direction. So if you have to move to here, and to move you have to reach there to get the maximum value. So this is the that's the intuition of the score function. So score matching it can be applied to the various isn't it? Various model like autoregressive model, energy based model, and normalizing flow. So why we need the score functions? So we have this we have developed this many approaches and and we have smartly mitigate some of these approaches and why we need the score matching we have GANs and other things we have different generative approaches, but why we need the this score matching why we need this score function. So as we know that deep this generative models field is just difficulty of dealing with the normalizing constant. What this normalizing constant is, uh, so this normalizing constant normalizes or makes the distribution uh, distribution one. So if you if you take the area under the curve, so if this is the probability distribution, and if you and we have to make this area normalized by 1, so we have to make the area under the curve 1. So this will make the area under the curve 1. So this if we divide with this normalizing constant, and it requires integration in higher spaces. So and if you make this area under the curve 1, so we can accurately estimate p theta of axis. And so we have to deal with this quantity, this z theta as so in case of energy based model, let's take the energy based model. So in energy based model we define p theta of axis and we'll with this notation so and this quantity is the integration of E of minus f theta of x and dx. So this is normalizing constant and which is intractable. So how can we get rid of this? So our question is, how can you get rid of this quantity which is intractable and which require a humongous amount of computation to deal with it? Score matching. So the approaches we are just looking at here is this: how can you make this quantity get rid of this quantity? So uh, we can take the gradients of this quantity. This if you take the gradient, if you take the log p theta of x and take the gradient of it, this will help us to get rid of this. So if you take the derivatives, take this gradient, not derivative, but this gradient with respect to x with log of p of x. We are not taking the gradient of this p of x, but we are taking the gradient of log of p of x. And if we take this, this is called a score function, and this give us this quantity which is not no longer dependent on this. So if you take the derivative, the gradient is become like this, the gradient become like this, and we are left with this quantity which no longer depend on the normalizing constant. This is just a the function f theta of x, and it is no longer depend on the this z theta which is the normalizing constant. So we get rid of this. So and we are not actually approximating the p of v theta of x, but we are approximating the log of we are approximating this quantity log of p theta of x, and this is we found that this quantity is equal to this gradient of f theta of x. This is just a model neural network function, so we can easily compute it. So and 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 we can do many things with this. So this if we have get the score, this if we have got the quantity, this quantity log of p theta of x, if you got this quantities we can do many things. So we can do various techniques like we can use this to generate samples using Langevin dynamics, and we can also apply the some of these SD approaches which require score while reversing the diffusion process is also. So we need these quantities in it to generate data. So you can just think like this quantity is very essential, and if it doesn't have the real p of x, it's okay. So we're gonna go employ this to generate samples and to make our generative models. So this is the main process of this here. So and 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 this is according to the slide is in the Yan song. So I will gonna show that slide. And so in 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 his slide isn't it? So if I can show you the slide, I think. So if I can show you the slide. So he give this approaches. So the main uh, benefit of us and main benefit of using this score based generative model is it actually allow three things according to him. And so this is the so he's I think the prominent people in the score based generative models, and he has written many papers. So and he say that it allows flexible model and improve generation and probability evaluations and controllable generation and accurate probability evaluations. So accuracy, better estimation of data probability. So if we have this, so we can just give some images and we can just evaluate the probability. So according to him, as so these are the some of the what you are saying is that if you able to score based generative model has this benefits, so it will improve the flexibility of the model. And it will do improve generations. So in control also it helps in controllable generations and also in the probability evaluations. I think you get the why we need the score function. So this is the idea as in what we need is in so why we need is and so how can we do this in so let me so start. So let's focus on this quantity. So just make it big. So we have the samples. We have some driven independently samples x1 x2 this which is from our data set. So we have the sample, and this is we have limited sample. We doesn't have the entire sample of the distribution. So and from that we want to estimate the this quantities in this grad log p data of x, grad log p data of x, and we want to so this is learning this quantity. Estimating this quantity is actually same as learning a vector valued functions. So we give this input images and it will give that same dimension score function like this. And this is our score model, and this is our probability density p of x, and we have this samples IID samples. So I think this is a independently uh, identically. So this is the sample just we doesn't depend on the any prior. So this is we just take some of the random sample from our distributions, because this is our images, our data distributions. So this is our images of the data distributions, and we want to approximate this quantity, this gradient with respect to the log p data of x. So we want to approximate this quantity, and but we can't actually we doesn't have the real sample. We just want to approximate through some neural network as theta. So our goal here is to we have given some samples from from some certain data distribution, and we have to learn this functions which will take this and give us this. This is called score models. And so let's understand it. So this is a actually if you consider this is a real gradient, this real vector valued function output. So you can just and this is our predicted output. So at the starting, so we started from this, and we want to approximate. We want to make this to as close as possible. So we will do some optimization here. This is the we will make this quantity align with this. This is a real gradient, and this is the our neural network, our model model vector field. And so this is what what why how can we optimize this quantity actually? Optimize this. So we will gonna optimize this Fisher divergence objective. So what it's actually say that, so we will gonna, this is a vector valued function, this is also a vector valued function. So and we want to make these two quantity equal, nearly equal, so our loss become minimum. So this is a real log of real, this is a real score function, and this is your model score functions, and we want to match this to quantity, and to match this, if we are able to match this, so our s theta will uh, approximately become equal to this real score of the density. So how can you optimize this? So this is a vector, so we will gonna go take some average Euclidean distance over the space. So we take the difference between this vector, and we're gonna go take the average of it. So if you take the difference, we'll take the average Euclidean distance over this space, and we're gonna optimize this, and we'll make this quantity as close to this quantity, and we make this vectoral alignment. So we want to make this quantity as like this quantity, so this original, so we want to push this vector towards the direction of this vector. So and if you optimize this, we'll certainly reach this. So we are taking the average Euclidean distance, and our first of all our goal is, let's find the square functions of certain data distribution. Suppose you have a distribution of cat, and you want to, first of all, let's, our goal is not to our goal is not to uh, our goal is not to directly generate sample, but our first goal is to approximate the this quantity, this gradient of the log of p of p data of x. So first of all our goal is, first of all find this, and we will move on to find later things in our way. So first of all our goal is to find this. So how can you find this? So 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 there is an objective called score matching. This was some in 2005. I think this paper has written. I forget the name, but this first paper is in the score matching papers. Have give some of the approaches here. And so in 2005, so they will gonna go do so. So this is we doesn't have we doesn't have this quantity actually. This is the, so how can you optimize this objective here? So our objective, we doesn't have the quantity, and we can't optimize this. So we, this is a neural network, and this is a real score function which we want to know, but we doesn't have access to it. So we will have to do something. How can you approximate this? And so how can you optimize this without knowing this? So this is the goal. So in score matching, some I didn't know the name of the guy right now. So this guy gave us the approaches, and which gives the formula like this. So this is a, so instead of writing this log of this, so we can decompose this by this. So if you try to decompose this, so this is a trace of the Jacobians. So there is no longer involvement of the this real real p data of x, and we can we will reduce to the this trace of the Jacobians, and this is, can be computed using back propagations, and this is our model. And if you take the back propagations, and if you take the back propagation, and you can just easily compute this quantity, but it has some challenges also. So and we get rid of this quantity here, we get rid of this quantity, and this is our objective right now. So we have left with this trace of Jacobians, and this quantity, and this quantity can be easily validated by the neural network, and this quantity is also can be validated by the neural network. And but it has some pitfalls. So problem with this is, approaches is that it is computationally overload, because as the number of dimensions grows and the back propagation step also grows. So this computation of this trace of Jacobian is highly computational intensive. So if your data dimensions, so I have given some of the link below, so references. So this is your neural network. So you can just calculate this quantity. This is a neural network. It takes some. This is the same dimension. So we have three input and three output. So mm, this is a RD cross RD. So what we are reading. So it will take the same dimension as the give takes same dimension input and give same dimension output, and we can easily compute this quantity as theta of x using some neural network. We can easily approximate with some neural network, and if you take the square norm, so L2 norm of L2 norm and square it, we can get this quantity as theta of x. We can easily get this quantity, and for this quantity, uh, uh, we have to do back propagations. So many back propagations. This is what I've written. So if I show you, how can you compute this trace of the Jacobian? So this quantity, if you take the, this is your score function, and if you take again the gradient, it becomes the Jacobians. So actually the Jacobian is actually the matrix, isn't it? So this is the, and matrix which contain the elements. The element of the matrix is actually a partial derivative. So we contain, this is the, and so, and how we compute this quantity. So we will take, first of all, let's consider the example of this because I have written it. So for the computation of this quantity, so we have to do back prop. So as I'm giving the arrow in this direction here, so you can just, so if I'm giving the arrow in this direction, and so if you want to compute the this quantity here, this Jacobian, this element, if you take the three dimensional, it will take nine elements. So first, second, third, and I'm just returning some of these. So this is a Jacobian. So and if you want to compute this element of the matrix, this ninth element of the matrix, and you have to compute back propagation. So how can you perform the back propagation like this? Yeah, that back propagation is like this. And if you want to evaluate this quantity, the last quantity, which is derivative of this theta as theta, so this quantity is actually as theta 3 of x3, and if we take the differential derivative with this, if we take that with respect to x3, so this, so this quantity here is actually this, so this quantity is computed by using some back propagation. So we do, so this quantity, and we have to compute all this matter. We doesn't have to compute, but because we are computing the trace, so we have to trace is actually what is trace. So and we are talking about trace of Jacobian. So trace of Jacobian. So Jacobian. So for the trace of Jacobian is just sum of these diagonal elements of the matrix. So we have to just compute the sum of these diagonal elements, and this will give us the trace of Jacobians. So as you can see here, so we have just three input dimensions. So what happen if our input grows? So the if our input if our the dimension of the input grows, we have to compute the back propagation. And so as you know, back propagation require derivatives, calculation of so many derivatives. So for the calculation of this derivative, it require higher other derivatives. We have to apply the chain rule of differentiations, and it require higher computations. So we have to calculate the derivatives so our derivative calculation becomes so much heavy. So as the dimension increase, the back propagation steps also increase with the dimension. So if you take the dimensions and if you take the back propagation steps, so if you take this two-dimensional graph, so it will grow linearly. So like this, and so this is a back propagation steps. So this is a back propagation steps. So back propagation steps. So and this problem. So if you increase the dimension of the data, it will go linearly. So this is the pitfall of this. this approach, score matching approach, which require the computation of the trace of Jacobian. So uh, Jacobian is just it contains the partial derivative and it contains the dimensions. So this we have three dimensions, so it is contains 3 cross 3 matrix, and this is not scalable for the high dimension we have, as we have seen. So score matching for high dimensional input is not scalable. So this is not scalable as the dimension grows. So and the other people in the score matching, so this is score matching, this is the 2005 paper, and in 2011 this guy Vincent wrote this paper, denoising score matching, and here, so we are, so to give you to concrete it, so we want to, so we are in the journey of learning the diffusion models. So in that we we are right now learning score matching. So score matching is, so this is a different, so we are, score matching is just we want to understand, we want to just learn this log of p data of x. So we are in the journey of learning this quantity. So we are not, so you can just think where what we are doing here is, and so we want to learn diffusion model, but this is, first of all we want to approximate this quantity, and these guys have given this, how can you approximate this quantity. So first of all we're going to understand this quantity, and then we understand how how diffusion models join into this score based generative modeling process. So first of all let's understand how can we match this, how can you do score matching. So in 2011 the Vincent released this paper, and so what he do is matching the score of a noise Petrov distribution. So what we are doing in above we are matching, so this is your data distributions p data of x. So we are taking the we are taking the gradient with respect to log of p of x, p data of x. So p data of x, so p data of x, so p data of x. So we are taking the this we are taking the gradient with respect to x, and this Vincent say that don't take the so first of all, this is a highly computationally, as we seen this require much more back propagation steps. So Vincent say that why we are, so we gonna go approximate the gradient of this noise Petrov distribution rather than which is smoother, because we add noise and our distribution become much more smoother also. So you can just imagine if we are Petroving, we're gonna add the noise. So this kernel here, this is a kernel like in CNN, this is a kernel which take the this quantity x, this real image x, and it will return this x tilde as which is the this image. So and this is the kernel, and this is a Gaussian kernel, so it will add Gaussian noise, and we are here, instead of approximating this gradient of log with respect to p data of x, so gradient of log of p data of x, we are approximating the gradient with respect to x of q sigma of x. So this q sigma is actually the intensity. You can just imagine like this is the intensity of the, why we are introducing this sigma is the intensity. You can just, intensity of the noise, how, what's the intensity of noise. So you can just consider, so the Vincent say that instead of approximating the real data distribution, real data distribution score function p data of x, take the gradient of this which is smoother, and how which is, and this is, and we're gonna go see some of the mathematical tricks. So here, so we are here, so we are comparing the, so we are now not learning the as theta of x. X is a real distribution, so this is a image of real distribution. So this is not a real image distribution. So we are not we are just comparing the as theta of x tilde, and this is a log of q sigma of x tilde. So this is a noise Petrov distribution. This is not an exact data distribution. This is a noise Petrov, means noise added distribution. So noise Petrov distributions, and this is the score of the score of the score of the noise Petrov distribution. So we are, rather than focusing on the actual p data of x, we are just comparing the score of the noise Petrov distribution. This is the original, and this is our model will predict this quantity. This, if you optimize this, we're gonna go approximate this as theta of x tilde nearly equal to this if you optimize it. And if I open this expectation in terms of integral and do some integration, and I actually read it if I integration, and I doesn't write the calculation here. So if I just open the integral and do calculations here, so I will eventually reach any. We also are going to apply some integration by part, I think. So if we do that, we're going to reach into this quantity. This x, this is you can just write this interchangeably. So because we are optimizing it, so here you can just don't be confused. So x theta of x tilde minus x tilde. So log of q sigma of x tilde given x. So this quantity is actually, so this is such a beautiful thing. So this becomes x tilde. So if you do some integration, and it will actually come into some reduction form, like this reduction form. So this become, so if you do calculation, this not interchangeably, but if you do calculation, you will reach this. Do some open the integration, you will reach this expression. And we are no longer with this distribution. This is, we are just, this is our kernel, the Gaussian kernel, so which add this noise. So we get rid of this noise bit of distribution, and which is even hard to approximate right now also, since so we just left with this kernel, which is a Gaussian kernel, and we are no longer with this q sigma of x tilde. So, and we get rid of this many challenges of, first of all, we doesn't have this gradient of the log of p data of x. We don't have this, so we try to solve using a trace of Jacobians, and trace of Jacobians is also hard. And in this denoising score matching, so we try to, this also we doesn't have access to this also. So if you simplify some of this, we will actually reach here, and we are just left with this kernel. So this is our score function, and this is our kernel, so which is simply Gaussian, and this kernel has this form, which has mean this and variance this, and this has the closed form solution, as you can see here. So this is x tilde minus x, it's also minus here, and x tilde minus x by sigma square. So we are just, this quantity is now tractable, and we doesn't have to deal with this another q sigma of x tilde distributions. So if I can, so now this is, so if you look at the benefit of using this, benefit of applying this denoising score matching, which is this quantity, what are the advantages of this? So what are the pros of this this pros of this, what are the pros of this? So we can select here. So this is scalable in high dimension, so it does not depend on the dimensionality, and it's just a Gaussian, and you can, and which has a closed form, so he doesn't have to deal with the dimensionality cross. And this is the, and this is tax is just, so denoising tax from score approximation, so we actually reduce this this score matching tax to denoising. So denoising means, so we'll look at it as how we reduce this tax of score approximation to denoising. And we know denoising is can be done using our neural networks, which are very good at it. So this is the benefit of using this. So it does not depend on dimensionality, and thus score approximation can be accomplished by the denoising tax. And we'll see how this denoising actually happens. So if we apply this formula, we actually reach there into the denoising objective, which we can apply our gigantic neural network to do the tasks. So what are the cons? So estimating the noise score of the noise Petrov distribution. Guys, we are not no longer estimating the actual this speed x. This is our real data distributions. We are not no longer estimating it, but we are estimating this quantity here. Log of q sigma. This is a Petrov distribution. So we are actually approximating this quantity here. So we are no longer approximating this, and our goal is not approximate this noise bit of distribution. So our goal is to approximate this, and we need this score, actual score. But we'll do some improvisation, and this is just take it. So this is the things you have to just remember. We are not actually estimating the true data distribution, but we are just approximating the Petrov data distribution. And what are the algorithms? So this is the algorithm of denoising score matching. So you can just do here. So if I can even make smaller. So this is the algorithm. So what is the algorithm for denoising score matching? So for denoising score matching, we will sample some of the data points. This from the real data distribution. This is our distribution of we're taking the images of cats. So if you we're going to sample the mini batch of data points like x1 x2, some discrete, not we have infinite, so we have some countable, so up to n. So we are sampling some of the data points mini batch. We are sampling the mini batch, and we're sampling the mini batch of the Petrov data points. So from this one, so if you so we're going to sample from this we're going to sample the mini batch of Petrov data points. So x from this distribution. So x tilde x this from this distribution, which is a the noisy version of this distribution, which is the noisy version of the distribution, and it will give this x tilde x2 tilde and this x n tilde. So where is my and and so so this is actually how can we sample from this is we're going to go apply the kernel, and we're going to go sample this x tilde this quantity here. So and third step of our algorithm, we're gonna go estimate the denoising score matching loss with empirical mean. So this is the same uh, Fisher divergence loss. So Fisher divergence in literature you can see that at a Fisher divergence. So this is so we want to minimize this objective. If we run the summation from I1 to n, and so this is because what we are doing here. So this is our neural network, and this is our the kernel. So this is our kernel. So which what this kernel do is it will take some image xi, and it will give x. So this is a kernel, and we know the kernel it has a closed form. So we know it has a closed form like this. So if you if you are write the formula here, so this loss become for the Gaussian perturbation. So if this quantity this kernel is actually a Gaussian kernel. So this is a kernel. So this if you consider it as a Gaussian, so it will have the closed form like this. We have already seen. So our if we consider it as a Gaussian, so our objective become this objective can be even simplified into this form, and we have to approximate. So we have to find the value of this quantity, and we have to find this optimal theta, which will minimize this overall loss. So and this is the I will tell you now how this tax is actually reducing a denoising tax. So this is our objective. So and this is a L to norm, and we are squaring it. So and this is and we're gonna go update theta with we can just apply some of the this optimize the using backpropagation using this SCD algorithm, this optimizer. So we can find the optimal value of this theta, which is a model parameter, and we will approximate at the end of the training. We will get this quantity x. We will get at the end of the training. We get the our score. We get our score of the noise as theta of x tilde. So we will get the best. If you train well, listen, we're gonna go approximate this quantity very quantity very accurately. So and this is the what is this quantity? This is the score of the score of the score of the p of x. This is not a score of p of x. This is score of the q sigma of x tilde. So and we are not right now approximating the real score, but we are approximating the score of some noisy. Some this is intensity. So we can just this is sigma. We're gonna understand sigma in detail, and it's a very important thing. So and what we are doing here, so we are approximating the score of this distribution. We are not approximating the real distribution p of x. So how it's converges into. So as I've seen, our tax is reduced in the denoising tax. So if you look at this as a denoiser, as a noise predictor or denoiser, so we know this quantity becomes this have this close this Gaussian, this a Gaussian, and which has a mean this and variance this. So and this q sigma is this distribution. So if I can just so so q sigma is have this form, and if we look at here, so score estimation. So how the score estimation actually happens. So 1 by 2. So we are just left with this. So this is our objective, and we can reduce into this form. So as I've shown you earlier. So if I show you earlier, so where we yeah. So here. So if you look carefully, so we're gonna obtain here. So we're gonna obtain here, and this expectation is what saying you are sampling x tilde from this distribution. So we are sampling x tilde from this distribution. So we are sampling x tilde from this distribution, and we are just optimizing it. So here uh, uh we what we are doing, we are sampling p of x, so which is our real image. So and we are adding noise using this. So this also we are introducing another expectation, and which will give us this x tilde, which is the real image, which is a real looking image. And in the real looking image, we're gonna go add some noise, and we're gonna obtain the x tilde. So from here we're gonna go obtain x tilde from here, and x from here. So this is if we write the expectation of x sample from p of x. So you can just this is the expectation, and what you're doing here. So this is just a scaling, so you can just consider that as a scaling, some sort of a scaling here. So and this is actually a noise. If you subtract it, you will get the noise. And this and what we are enforcing this as theta to become is the noise. This is a noise, and we are if you want to minimize this whole objective, if you want to optimize the whole objective, is as theta x tilde should predict the noise. So what we are learning here, guys, we're actually learning the neural network, which is a noise predictor. How much noise is added, isn't it? So So this will give noise. So if you subtract this quantity with this, you will get noise. And if you do I'm just doing subtraction, and you'll get the noise. So we are building the noise predictor here. So you can get some of the connection here. So in the diffusion series, we see that this epsilon theta, which is a noise predictor, is actually our neural network, and which will help us to calculate the mean. So this is some, again, as you've seen some of the connection here also. So this is the we reduce the tasks into noise prediction. So this is our and to understand it much clearly. So there is Tweedie's formula. So what is this Tweedie's formula actually is? So according to this formula, the optimal denoising strategy is to follow the gradient. Is to follow the gradient or score. So if we want to denoise means if you want to get good samples, follow the gradients. So what is the gradients? Gradient is here. So if I show you here, so here, if you want to denoise it, go follow the gradient and take the reals. And this is the real. So what is this gradient? So this 2D's formula actually say that if you want to get good looking sample, follow these gradients and you will get good samples. So this is the 2D's formula what is saying. And if I bring you where we are, so where here, so according to 2D's formula, the optimal strategy is to follow the not noisy gradient, but the gradient. So and what you're doing is actually you can see here. So according to this formula, what is saying, find if we have the x tilde. So if you want the x, you will sample from this distribution, mm, some p of x given x tilde, and you just want to get the x which is real. So what you have to do, you have to move to the directions by this. So you have to go the direction towards towards the score. So if you follow the gradient, you will approximately reach some of the distribution, underlying distribution. So if you follow the gradient, you will gonna go reach. So this is the idea. So what we're doing, we are adding this axe till some noisy image, and we're gonna follow the gradient. So this is if you want to axe. So if you want to denoise, so we have to follow this gradient. Follow this enough, we will gonna go certainly reach. If our gradients are in right direction, if our gradients are in right direction, we'll certainly reach our zone where the noise free image lies, where the good image lies. And and this is the 2D's formula. So this give us how can we find x, and we can go to the best x which is a noise free by using these approaches. So guys, let's look at this paper is new, which has been written in 2019. This slice score matching, and this is written by Yan Song and other collaborator. And the slice score matching is a really efficient technique. So what this actually says, if you have this is your real score and this is your model score, and if these two are equal, then the projection on any arbitrary line, this if you take, so this is your vectors, and if you take the projection here also, if you take the projection here, then the projection should match. So projection on this arbitrary line and this projection on this arbitrary line should match. If you take the projection on this so consider a projection onto a random direction. So if you take this, in case of this, if you take the projection, then the projection on this line should match. The projection on this line should match. And this is the problem reduced into this projection matching from. And there are also some pitfalls. We are not matching the actual score, but we are matching the projection. So we are reducing the problem into projection space, and it will create out some problem, but it actually reduces the problem into one dimensional. Rather than dealing with the multiple dimension, we just projections, consider random projection on random directions, And the main approach is, so we'll not we'll just compare the projection right now. So our objective is match the projection. So like in our objective, so projection 1, so projection 1 minus projection 2, our objective become like this. So in our above objective, so if this both projections are equal, then our zero, and this is our objective to make. So this is our objective, but we will not actually, we can't make this as zero, but we'll optimize. So we'll minimize this objective, and we'll find the we will reduce the problem of projection into the projection space. And for this, we need different term, and there need some modal parameter theta also. So our problem is reducing some projection space. So this is the gradient of log p theta of x, and this is, so what you are saying is, if you have this, and this will have the projection like this. So so if projection on the direction should be same. So if this hold true, then the projection on the any random direction should be same. So and projection space is efficient because it's reduces into one, this is one dimension, and this is the object, this is the projection one, this is the projection, and this is a real projection. So this is our projection on this data space. So this is above one, and this is the projection then above one, and this is the projection of, if you take vt, and as you know that if you do dot products in it, dot product is actually the projection. What you're doing here, just dot product between this random vector v, random which has been sampled. So this is actually a v, guys, not x, this is v. So we're going to sample from this pv, will sample some random vector v, and this is a p1, this is a projection of the score on this vector v, and this is the projection on the same vector v, and this is the our model, and this is our objective return, the score of the objective of slice score matching reduces to this. And if you take this quantity is projection 1, this quantity is projection 2, and if you able to match this both projection equal, then this is your objective right now to make. And this is also called slice Fisher divergence. And so solving more by integrating by parts, you will get this quantity here. So we doesn't have this quantity actually, so we want to approximate this quantity by this, by as theta, but we want to make as theta close to this, but we doesn't have the access with this. So we gonna replace in terms of some as theta or other parameters. So if you replace this quantity doing some integration by part, so we will finally reach this objective here. This is uh, our objective become like this. So we write this quantity as, so this is the same as, so our objective becomes changes. So if we do open the expectation and do some integration by parts, you will get this objective. And and this also involves Jacobian calculations, and this quantity is actually, so our objective is this, and this involves Jacobian calculation again, but this is not a, so this is a vector Jacobian. So our objective become the Jacobian vector product, and which is actually called a directional derivative. So this quantity here is, this is a v, this is a v, and this is the score, the gradient. This is the Jacobian gradient of x, gradient with respect to x of s theta of x, and this is the transpose of b. And if you, this is actually called Jacobian vector product, and it is same as the directional derivatives. And and this is actually easy to compute because uh, I will see the region as you go. So it can be easily computed with back propagation. So we can compute easily with the backpropagation and computing vector Jacobian vector product is scalable to high dimensions. So how is it scalable? So we'll see. So as I'm saying that vector Jacobian vector product is efficient, and this calculations this this calculation is, we can just rewrite this as this quantity here. So and this quantity is actually become this. So we gonna go apply the neural network to compute this, and I'm saying that it's high, this is scalable. This Jacobian vector product is scalable into a high dimension, and I will show that how it's scalable in high dimensions. So for the so we are computing this quantity, and for the we gonna go first of all find this quantity as theta, and this as theta can be easily computed just from a one single feed forward. Do some forward propagation, you will get this as theta of x, and after that you add just one node to this dot product operation. So we are doing just projections. So this is actually the dot product, and as you can know that dot product projections is related to the dot product, and so this is just doing some projection here, just doing dot product between these two vector, and you will this is actually become scalar, because as you know, when you do dot product with two vector, you will get the value of the dot product is always a scalar, because you do element wise operation and you add each element. So if you take just, so if I show you this element, this is the, if you do the dot product with this, so it is just one dimension, so you will get some scalar values. So you're gonna add the element by each. So this is the dot product, you will get some scalar value here, and after that this operation is actually give you some scalar quantity, which is certain scalar, this is this whole quantity becoming scalar functions, and you are taking the, you are right now not taking the gradient, you are not taking the gradient with respect to x. This is the vector valued function, this is, and but you are having this quantity which is of scalar functions, and while taking the you can just do one single backpropagation to calculate this quantity. This is scalar functions, and you can just take the gradient with respect to x, and you get the you get this quantity, which is the gradient of the scalar function, this scalar functions, and you and we have computed till this part here. So if I show you, so we have computed this part. So we have computed this part, and we computed this, and and we have also do this. So we have computed this part now, guys. So I have computed, so this part we have computed, and after that we have to compute this b. So b is also dot product. So we are, what are we doing? Nothing, just a dot product here. Dot product between this quantity, which is the gradient of the scalar functions, and which is easy to compute. So this quantity is actually easy to compute because this is also scalar functions, and while computing the gradient of this vector valued function, this as theta is difficult, but for the calculation of this, for the calculation, so we are doing this bt into as theta. So this will, we have already done it. So we're going to add this some node here, and we're going to multiply by this b. So add this node and just take the output from there and multiply with this bt. So one propagation is sufficient, and this is a little bit slightly slower than denoising square matching, because we have to compute back propagation. So this is I think that very easy. This is not if as efficient as the efficient, not means efficient, this is efficient but not as faster as the denoising square matching. This is the one of the cons of this slice square matching, and how it's perform, and if you want to just make an algorithm and just run it, how can you do it? So what you're doing here is just so I will take some of the other color. So I'll take this color. So let's start. So so what you're doing here, so we will gonna sample a mini batch of data, so which is this, and this is, and we're gonna sample a mini batch of projection. So this is the P1, P2 from PV, and you can just sample one also, one projection also, but if you want to boost the performances of as I've written, so if you want, so what you're doing here, just we are sampling the projection. You can just sample one also, one is sufficient. But if you sample this more, so if you can use more projection for data points, to be the to boost your performances. So as you can just sample, so one is sufficient, but as you can, so for data points, so if you sample much more, so you gonna go boost your performances, but your computational will be increased. This is the trade-off. So and we're gonna go match the, so as we take much more project progression, our accuracy becomes higher, but our computational, this is a trade-off. So and what we are left with, so we sample some of this projection vector. This is a random vectors, and this is the data, and this is the objective. This is the some projection. So from I to n, I'm running it with summation here, and just taking, so this is, and just dividing it 1 by n. And what I'm doing here, so our objective, this is our objective, and I have to find the optimal value of theta, and I have to, so what I'm doing here, so I'm just taking some vector v1 and um, doing calculations, because this is not comprehensible or understandable, because this is has been solved by integration by part. So if you optimize this expression, you we will gonna go, this is score matching loss. So if you minimize this loss, we're gonna go find the optimal value of theta, and it will give, and it will help us to determine this quantity as theta of xi, and we're gonna go approximate this as theta. And you can just, projection distribution can be so you can sample this projection from this projection vector, this sampling. So what are sampling here, so the sampling, you can just do sampling from this projection distribution, can be this Gaussian, this PB distribution can be Gaussian, and this radar matcher. So you can just do it, and this, so let's move into the experimental section. So in the first graph, as the dimension increases, the this second spot iterations also increases rapidly. This second spot iteration, and our memory will run out, and we need more computational resources. So and this is the, and this is a slice version, and which is steadily with the data dimension. It does not get affected by the data dimensions. So and in the density estimation, if you see in the density estimation, so this the slice versions actually approximate the actual density. And let's look at the this part, which is inferencing or sampling from this score based modeling. So the pipeline, just look at it. So we can just look at it. Score based generative modeling is, we have some samples from this distribution p of p data of x, and we take some samples and we try to approximate the score using score matching. We can use denoising score matching, or slice score matching, and we have to approximate this quantity as a theta, and from this data per data we have. So and the data actually come from the p data distributions. So we're gonna approximate this score, and we're using this score, we're gonna go generate new samples. And how can you do this, how can you do sampling from the how can you sample from the score. So we have some samples, we find the score using neural network as theta of x, and we want to generate samples. So for sampling from the score, so we have nothing but just a score, this as theta of x, here. So and it is a bimodal distribution which has this two mode here. This is the high density, so there is also the high density. So data, how data from distribution lies here and here, and we gonna go initialize some particle here, and we're gonna go follow the score. So if you follow the score, we will if you run this dynamics, so what we see is as we run it, it will gonna go approximate, it will move to us. If you follow the this vector field, this direction of the vector, so if you follow this direction of the vector, and we're gonna approximately reach the actual density. And if you consider this as, and we will gonna go, if you run enough, then we will gonna converge to the peak point. So here, so which is just if you have this distribution, so this is multimodal distribution. As you can see here, we have here and there two mode, and in case you can consider like this. So if you apply this quantity, this if you just follow the score, this vector, if you just follow the vector and move to the direction given by the vector, you will gonna go as we run it enough, so you will gonna go reach from here to here and then here. So here the all data points are overlapping each other, so we are just at the peak of it. So if you consider this as a, it has two mode, you can see here it has two mode. So here also it has two modes. So if you apply this, if you just follow the score, we will gonna go reach at this, so all points will overlap at the peak, as we can see here. Or and we doesn't want that, we don't know, we want the probability masses given to the whole space, so we doesn't want all point to overlap here. So we gonna, there is some pitfalls in here. So this is not, so right way to samples is to follow the gradient. Gradient means the score this vector. So and and this has some weak, so this will not gonna help us to put the probability mass to the to our data distribution. So and we're gonna go follow the noisy gradient, which is actually called Langevin. So Langevin, this, so we're gonna go applying the Langevin MCMCs. This is a Langevin markup chain Monte Carlo, and which is a sampling procedure. So we're gonna apply this, and we have what we do here in Langevin MCMC. So we gonna go we gonna follow the noisy score rather than following just the score. This direction of the vector, we're gonna follow the noisy score. And what this noisy means, we're gonna understand that. So if you can, if I can show you, so we're gonna initialize some particle here, and this is just a point. So so you can, so this is a point, and if you follow the noisy score, you will gonna go reach. So if you run this dynamics enough, so you will gonna go, so we're gonna go closer to the actual distribution. And if you enough follow this, you will gonna go have this. So the data points is actually covering the actual distribution mode of the distributions. So also there are also modes of the distribution here, they are also covering the mode of distributions. And you get the probability mass in the, not only at the peak. So here in this case, you are not just giving the probability mass like here. So you are giving the probability mass in this space, so you are giving the probability mass in this space, this. So this is the, so you are giving the probability mass to this space. And so you get, if you apply this Langevin MCMC, you will gonna get the, you will gonna go obtain the samples at the right point. So so what's this, how can you follow the, what is mean by following the noisy score? So noisy score means, in the previous one we just take the take the sample at the time t, and just follow the score, just epsilon by 2 as theta and x t tilt and plus this epsilon root over epsilon zt. So this is the noise addition. So we are not only following the score, so this xt point is not only following the score, but it's also following the noisy score. So we are adding this noise, which is sample from this distribution, which is the pure Gaussian distributions. So if you run enough, this procedure it is guaranteed to sample from a distribution p of x. So and it in the theory is so if this value of epsilon tends to 0 and t tends to infinity, it will guarantee that we're gonna sample from this distribution p of x. So and for that, so here is called something called Langevin dynamic sampling. So it is just giving some algorithm for us to operate. So if I show you, so your so what are you gonna go do? So this Langevin dynamic sampling is actually performed when you want to sample from this p of x using only the score. So guys, we have just a score. We doesn't have anything, so we have a score. This the gradient with respect to gradient with respect to x log of p of x. So and this is a this is a vector field, and we have only this vector field, and we want to sample from the distribution p of x. So for that we're going to go initialize some points. So x0, which is from this prior, so this pi x, and we're going to initialize this, and what are we going to do, we're going to go apply this Langevin MCMC, which is take the previous image, follow the score, and also follow, not just only follow the score this quantity, but also follow the noisy score. So what we're doing here, so from t1 to t, we are sampling some noise here and taking the previous one and just adding with some score and also following the noisy gradient here. So not only this is just a score, so we does not only follow in the score, but we are also adding noise. So this xt minus 1 will also, we are pushing to the direction of the noisy score, not the actual score. So and and this procedure is, so if this epsilon tends to 0 means, if this quantity epsilon tends to 0 means this noise will be removed, and if t tends to infinity, we are guaranteed to have the xt, this last time step output will be from the p of x distribution, which is our required distribution we want to sample. So and if this condition holds, so if theta is, if the model is trained well, if the model is trained well, if this quantity as theta of x nearly equal to gradient with a stack of log of p of x, then we are guaranteed to sample this xt from this p of x. And and there is, so what we're doing here, so we are the first of all we're gonna go approximate, gonna go work on this score estimation, which can be done by denoising score matching, slice score matching. So first of all we're gonna go estimate the score, and after estimating the score we're gonna go employ Langevin dynamic sampling, and we're gonna go make the generative model which is used to sample from p of x. So, to generate samples from the distribution p of x. So, first of all, our goal is to find the score of the any distribution p of x. So, p of x can be the distribution of images of cat, dog, and anything it can be. So, and also p of x, it can be the distribution of anything. We're gonna find this quantity using the our neural network as theta of x, and this quantity we're gonna approximate this quantity as less as theta of x, and using this score, this gradient, log of p of x, we're gonna go employ Langevin dynamics. And this Langevin dynamics is, if we in the limiting sense, so if t tends to infinity and this epsilon tends to 0, then it ensure that we are guaranteed to sample data from p of x. So this is the overall picture. So let's understand the pipelines of this score-based generative modeling. So what we have. So let's look at the pipeline of it. So what we're doing here, guys, is just this is a score-based generative modeling. So this is another realm, not the diffusion, but this approach is will gonna go masked. So this approach is will gonna connect to the diffusion. If we go forward enough, and so we're gonna go take some samples, x1, x2, and so this is our data set, and it has some data samples. We doesn't have the complete data sample. We have some data from this distributions, and from this data we gonna approximate the score. So from this data, which is lie in our training set, so from the data we're gonna go approximate the score, and for the approximation of score we're gonna go as we know that the neural networks are the universal function approximator, and this is a vector valued function. So our neural networks can also map also approximate this vector valued function. So we're gonna go applying the neural network to approximate as this quantity, this gradient x log of p data of x, and our neural network will gonna go approximate this vector valued functions, which is a score. So and if we approximate the score, we can, as we know that this Paul Langevin see that doesn't if you have the gradient log of, if you have the gradient if you have the gradient log of this is a log of p of x. So or the Langevin say is that if you have the gradient, uh, you are capable of sampling from the distribution p of x. So if you have this quantity, you can sample the data from these distributions, if you run enough the required steps. So and you will gonna go employ Langevin dynamics and you will generate samples. So this is the overall pipeline. And if I so I wanted to say that, so our first what we do is, and so before going to that is, and so first of all we work on score estimations. So we first of all we work on score estimations. So for the score estimation, we start with the score matching, then which has been in I think it's 2005 paper. So this is a score matching paper 2005, and then this is the first paper, and in the second paper we see that Vincent paper denoising score matching, and the third, we see that the the slice score matching. So and this is going to help us to estimate the score. So these are these score estimation techniques. So the slice score matching. So score matching. So if I slice score matching, so slice score. So this is slice score matching, and this is the RSH score. We're gonna go apply this techniques to, and we find that this approaches work better, and we do once we find the score, this quantity gradient of x log of p of x, we're gonna go approximate. We're gonna find this quantity using this approaches, and if you have the score, we can employ Langevin sampling. So for the Langevin sampling, so according to Tweedy's formula, so Tweedy's formula say that we, as you have read, Tweedy's formula say that follow the gradients, and but so while employing Langevin sampling, Langevin MCMC, so we have to follow the noisy score rather than following the just score. We're gonna go follow the noisy score, and it will gonna go uh, it will gonna approximate it will gonna go initialize that particle towards the distribution as I've shown here. So not only just all points are overlap, but this helps to just make the point not just overlap into one point, just a minima or just maxima. You can just in some maxima, but it will gonna go inside the particle. Like here is this following the noisy score. So and if I so 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 if you imply Langevin sampling and follow the noisy score, you will gonna put the probability mass to the to the spaces where the actual space, not the just a point, particular point, all data point overlapping. So first of all, we're gonna go approximate this score and employ Langevin sampling. So and if you just apply this thing, so you will get the result like this. So and from this results you can see that we are missing something, and we do as we move, and we will, so we are in a track of making this score matching more practical. But right now we are just, so there are some pitfall here. So there are some we are something missing, so we are missing something, so we are missing something, and so we are missing something. So and and in the next video, and we're gonna see why we get this results. So and we go from square matching to slide square matching, and from so we apply this Langevin sampling, and we even get the samples. So there are some pitfalls in our score estimation. So in the next video we're gonna see how can you deal with this